All right, so chapter 40 is all about hemostasis coagulation. So we are going to go through what exactly hemostasis is. So hemostasis is just our body's way of making sure that your blood stays liquid in your veins and arteries and not clotted. It prevents us from having blood loss from injuries. It helps reestablish your blood flow while you're healing. And anytime that hemostasis is out of balance, you can have one of two things occur. You can either go to the clotting side or you can go to the bleeding side, depending on what's going on. So thrombosis means clot and hemorrhage means bleeding. All right, let's go to the next slide here. So the cell elements that are involved in hemostasis are your platelets, of course. We all know that platelets have a role of clotting. Your vascular intima, which is basically like your blood vessel lining, plays a role. And then red cells and neutrophils and monocytes can even have a role in the clotting process. So let's take a look here at what we call primary and secondary hemostasis. So primary is all about small injuries, whereas secondary is larger injuries, if you will. So in the primary, with the small injuries, your blood vessel is actually, this is where that vascular intima comes into play. It's going to contract and seal over that wound. And then the platelets will come up and form a plug and help clot it. So in the primary, it's definitely the vascular intima and the platelets that are involved. In the secondary hemostasis, we have a larger wound, and so more bleeding. So we need more than just platelets to control that. Platelets aren't going to solve it all. So this is where we get into what we call coagulation proteins. We have 16 different coagulation proteins, and that's what we're really going to talk about in this chapter today. So those coagulation proteins are going to work together to form what we call a fibrin clot. So that clot, that fibrin clot is going to be able to help heal that larger wound better than just platelets would be able to. And then let's quickly talk about the red cells and monocytes and stuff that I mentioned earlier. The way that they play a role in this is red cells will come along to that fibrin clot and just add more structure and bulk to it to make it bigger and more stable. And then the monocytes and lymphocytes play a role with inflammation and triggering the coagulation. Okay, so do we have any questions yet on just the background information of what hemostasis is? You feel okay? All right, I'm going to assume that's okay. So, not yet. Okay, great. All right, so coag factors. Let's get into our actual coagulation proteins. So, again, there's 16 proteins. And guess where they're made? When you think back to chemistry, where were all our proteins made? In the liver. So these proteins are going to be made in the liver, and they work together. Basically, they go in a series. It's kind of very similar to complement. You guys just learned about complement, where it's like each step needs to activate the next step. It's going to be really similar to that. Each protein is needed to activate the next protein to get to our end goal of a fibrin clot. Just quick note here, these proteins, these coagulation proteins, we call them factors, the same thing, proteins are factors, and we actually number them with Roman numerals. You never thought you'd see Roman numerals again? Well, here they are. Hopefully you guys feel comfortable identifying Roman numerals. If you don't feel badly. We can talk about them. Just remember that V is 5, X is 10, and so if you have any questions on the Roman numerals, please ask, or you can also ask your lab instructor, Kim, that are also. So the other quick note is anytime that one of these proteins or factors becomes activated, they're going to place a little A after the Roman numeral to indicate that it's activated. So I have an example there. Factor 7 goes to 7A, meaning that 7 has now been activated. All right, so here's all your proteins. And lucky for us, you have to know both names. You have to know that factor 1 is fibrinogen. That factor 2 is prothrombin. You know, factor 9 is everybody's favorite Christmas. So definitely know both names. I will give you a clue that next week's quiz has several questions on just this, saying, hey, what's factor 4? It's calcium. What's, and so on. This is a great way to do flashcards just by making out the flashcard, put a factor, the Roman numeral on one side and the actual name on the other, and then you can have anybody quiz you. And then you have those flashcards forever to keep reminding yourself. There is a couple here that don't actually have Roman numerals, prekallikrein and high molecular weight kininogen. The high molecular weight kininogen, the initials we use for it is HMWK. So whenever you see HMWK, it's referring to that. They actually do have another name, Fletcher and Fitzgerald, so just keep that in mind as well. All right, so when I get going in the pathways here, you'll hear me referring mostly to these by the Roman numerals. There's a couple that I'm going to refer to by name as well. The big ones that really are commonly used by name is fibrinogen, which is factor 1, and prothrombin, which is factor 2. We a lot of times hear those names called out instead of just the factor Roman numerals, so make sure you're familiar with those two. And then the other one is this factor 3, tissue factor. Most people just call it tissue factor. And so just kind of a clue on those. All right, so let's get going. We have two coagulation pathways, the extrinsic and the intrinsic. There is another name for the extrinsic pathway, and that's the tissue factor pathway. So I put down here what activates each one. It's important that you know what activates each pathway. In the extrinsic tissue factor pathway, it is activated by a tissue injury, so a wound, would you say. And when you have that injury, the tissue factor, factor 3, is found in the tissues, and it becomes exposed, and that triggers our extrinsic pathway. I put down the factors and the order in which they occur in the extrinsic pathway. So the ones that are involved in extrinsic are 7, 10, 5, 2, and 1, and that's kind of the order they're going to go in. And we'll look closer at this pathway here in just a second. In the intrinsic pathway, this is activated by contact with a foreign material, say like a prosthetic heart valve, for example. And there's quite a few more factors involved in the intrinsic pathway. It's 12, 11, 9, 8, 10, 5, 2, 1. And of course, like anything in lab, it never goes in the numerical order. But out of the two pathways, extrinsic and intrinsic, do you notice some factors are the same in each and the same order in each? Awesome. 10, 5, 2, and 1. Good. That is what we call our common pathway. I didn't write that on here, but definitely know that 10, 5, 2, and 1 is the common pathway. It's not really another pathway. It's just called the common pathway because it's common. It occurs in both extrinsic and intrinsic pathways. But if you ever hear of the common pathway, that's what it's referring to as 10, 5, 2, and 1. All right, so let's get started into our pathways. The first step is extrinsic pathway. It's the shorter one. Again, remember, this is getting activated by a tissue injury, and that tissue factor starts the whole process. So how does the tissue factor start our process? Tissue factor, which I have identified as TF right there, activates factor 7, which is our very first factor in this pathway. So that's why it's above the little arrow there. So 7 becomes activated. See the little A after 7. That's how we know it's activated. So that tissue factor activates factor 7 after the tissue injury. Factor 7 then activates factor 10. So remember, each step activates the next. So factor 7 activates factor 10. 10, along with the help of 5, so the two of them together, very important to note that 5 is a little bit on, has to be helping 10 to activate the next step, activates factor 2, which is our prothrombin factor. Factor 2, when it becomes activated, it is actually now called thrombin. And so you hear a lot about thrombin, so make sure that you know when factor 2 is activated, it is called thrombin. That thrombin then will go and activate factor 1, which is our fibrinogen. And when you look at the word fibrinogen, the biggest part of that word that stands out is fibrin. And that is actually what makes up our clots. So now we can have a clot occur. So that's great. We've achieved our goal, but we're not quite done yet. we have to stabilize that clot and make sure that it's truly stable and structured and ready to go and help us heal. So what helps stabilize it is factor 13 right there. So factor 13 is only role is to stabilize that clot. And factor 13 actually does get activated by thrombin. That's why you see the thrombin on a diagonal right here. And I'm sorry, just a second. Hannah, no. Go then. Fine. Okay. So, gotta love kids. Anyway, so that thrombin activates factor 13 as well so that it can come along and stabilize the fibrin clots. So that is basically your extrinsic pathway. The way that I learned this in college is I simply wrote it out over and over and over again until it flowed. Or you can keep it simple, and as long as you know the steps, that it's 7, 10, 5, 2, 1 clots, and that you know where the 5 sits in and that 13 sits in. You can try to simplify it down to that if you'd like, but make sure for your quiz that you can list the factors involved in this pathway and the order that they go in. So that's really important to note. Are there any questions on this pathway, or do you guys want me to repeat it or repeat any parts of it? Awesome. Okay. So let's go into our next pathway, which is the intrinsic pathway. So again, this one has a few more steps to it, but the nice part is that when it gets into the factor 10 area right here and down, it's the exact same thing. So you just have to learn the beginning, which is different. So remember, intrinsic pathway gets started by contact with a foreign material. So the very first factor that begins is factor 12. And factor 12 needs the help of HMWK and pre-K. They help activate it. So all three of those kind of go together there to get 12 activated. 12 then activates 11. 11 then activates 9. And 9, along with the help of 8, it has to have the help of 8 right there, activates our 10. And then the rest of it is the exact same as the extrinsic. So 10, along with the help of 5, remember, has to have the help of 5 to activate our prothrombin factor 2. Again, when 2 becomes activated, it turns into thrombin. Thrombin helps activate our factor 1, which is fibrinogen. And again, fibrinogen is fibrin. That's what makes our clot. And then again, we have to stabilize it with the help of factor 13. So again, write it all out many times over and over again. They look really complex, but they're truly pretty simple as long as you know the order and the factors involved. So in this case, it's going to be 12 with HMWK and pre-K, 11, 9, 8, 10, 5, 2, 1 clots, along with the help of 13 at the end. So those are your two pathways that you have to know. Questions on those? Do you think that, do you want me to repeat anything again? I don't want to, I can't hear you, so I want to make sure that you feel comfortable. I'm going to take that you might be okay. Awesome. Okay, good. So now that we've covered both pathways, let's talk a bit about some key components of each of those factors. So we've already introduced hemostasis. We talked about that there's 16 coagulation factor proteins. We talked about the two pathways and how they occur. So now we're going to take those different factors that we've been discussing and break them into groups, and also just talk about a few key components that we haven't mentioned as much. So there is a group of factors called the contact factors, and those contact factor group is 12, HMWK, pre-K, and 11. So what pathway does those occur in, the 12, HMWK, pre-K, and 11? Awesome. Intrinsic. And do you remember what starts intrinsic pathway? What activates it? So these are the first four factors in the intrinsic pathway. So what activates the intrinsic pathway again? Good. So contact with a foreign material or foreign object. So that makes sense why the first four factors in the intrinsic pathway are called the contact factors because the whole pathway gets activated by contact with the foreign surface. So that's a way to put that together. Another group that you should be aware of is what we call serine proteases. Basically, these factors can act somewhat like enzymes when they want and go and cleave bonds. That's what it means to be a serine protease, is they go and cleave bonds. So the ones that can act like that are 7, 9 through 12, basically. So it's 7, 9, 10, 11, 12, and thrombin. So you just need to know that they can be serine proteases. Again, remember on factor 13, the whole role of factor 13 is to stabilize or provide strength to the clot at the end. And actually, when you go to that big chart that had the names on it, you'll note that for factor 13, its name is fibrin stabilizing factor. So it tells you right by its name what it does. Calcium and phospholipids. Now, I didn't put these on my pathways, but they're extremely important parts of our coagulation pathways. And actually, calcium is also called factor 4. But we have to have both calcium and phospholipids present in order to have a clotting pathway. If you don't have calcium or phospholipids present, you cannot have your coagulation pathway occur. Think back to phlebotomy. When you guys learned about the tubes in phlebotomy, the anticoagulants like EDTA, sodium citrate, the whole purpose of those tubes, right, being an anticoagulant tube, is to keep the blood liquid so that it didn't clot. Well, how did those anticoagulants work? Well, EDTA, sodium citrate, they both bind calcium. By binding calcium and taking that out, they were able to make it so that the blood wouldn't clot. So that should be a direct correlation for you guys to know why we need calcium and then also phospholipids. If we have those, we can have a coagulation pathway. If we don't, we're not going to be able to go through our coagulation pathway. So again, these are very important parts of the steps in those pathways. I just didn't add them in there when I was showing them to you. There's a quick factor that I want to talk about that we haven't mentioned yet. It's not in the pathways at all, but it is an important factor in our body in regards to just our whole coagulation system, and it's von Willebrand factor. The initials for that would be VWF. Von Willebrand factor actually is carried inside the platelets and some of the granules. It has a huge role with platelet adhesion or the stickiness of platelets. And then it also will carry and stabilize factor 8 for us. So that's its two main roles that you should remember about the von Willebrand factor. And then last one on this slide is fibrinogen. We talked about fibrinogen and how that makes our fibrin clot in the pathways, but it also has another role. It also can be found in the platelet granules, and it has a huge role in platelet aggregation. In other words, how those platelets clump together or aggregate. So make sure that you also know that other role of fibrinogen. Let's keep going here with our key components. The next group that you must know is the prothrombin group, and this contains factors 2, 7, 9, and 10. I know that there's a quiz question on this. It might not be next week, but it's somewhere along the way that there's quiz questions on this group. The prothrombin group, these factors 2, 7, 9, and 10, are what we call vitamin K dependent factors. In other words, they need vitamin K in order to function and help us clot. Why is this important? Basically, you guys have probably all heard of warfarin medicine or Coumadin medicine. A lot of people take it. It's what you could call it a blood thinner, if you will. There's different reasons people may take this medicine, but anyway, it makes it so that they don't clot. It prevents them from clotting. That's why it's called the blood thinner. How this medicine works, how warfarin and Coumadin work, is that they are a vitamin K antagonist. So when somebody takes that medicine, it will go and basically block the action of vitamin K so that vitamin K can't be used to help the factors 2, 7, 9, and 10. And if those factors can't use vitamin K, then we can't have them in our pathway getting us a clot. So that's how warfarin and Coumadin make it so that those people can't form clots, especially if they're prone to forming clots. So be sure that you know that prothrombin group and how the warfarin Coumadin action works on it. And then lastly, I wanted to mention thrombin. Thrombin has a lot of roles in our body. You saw that it's in both pathways, and it helps us activate fibrinogen, which is factor 1. And I didn't list that on here, but factor 1 is activated by thrombin, as you saw in those pathways. But it also activates a lot of other things. It activates factor 5, 8, 11, and 13. And then it also activates protein C, which we haven't talked about yet. We will get to protein C here in a couple slides, but basically thrombin will bind with thrombomodulin, and protein C will become activated as a result. And I know that's a question along some points, but just know the role of thrombin and all the things that it can do and activate. All right, so we basically talked about the pathways. We talked about the extrinsic and intrinsic and how we can form a clot. But what do you do with those clots after they're formed? You can't just have them sit there, because we would all have clots all over our body and we wouldn't be able to live. So something has to get rid of the clots, and that's our fibrinolysis pathway. If you just look at the title fibrinolysis, lysis means breakdown, and it's got fibrin right in it. So it's the breakdown of fibrin. So this pathway is what will digest and get rid of the clots. So there's only 2 steps here. Plasminogen will convert into plasmin, and plasmin is what digests the clots. That's it. So you just need to know the parts of the fibrinolysis pathway and what fibrinolysis means. And it means just to break down and get rid of the clots for us. One little thing here on that is when we break down that clot and digest it, we get some pieces of that digested clot, which are called fibrin degradation products, FDP. If you think of it this way, when you eat a cookie, you're going to get crumbs of the cookie. You can't just get all of it meticulously in your mouth, or at least I can't. So think of it the same way for your clots. When you eat a clot, digest a clot, you're going to get little pieces still coming off of it, little crumbs. So that's what the fibrin degradation products are. There's one type of piece of the clot that's important in the lab, and that clot, that little piece is labeled D/D, or what we can call a D dimer. A D dimer is a really important test. It's seen a lot ordered through the ER. So if a patient were to present to the ER and that doctor feels like they might have a clot occurring, whether it be a pulmonary emboli, a deep vein thrombosis, whatever, they can order up a D dimer and we can run it. And if that D dimer is high or very positive, that tells the doctor that, yes, that person does have a clot or clots occurring. So again, a D dimer is a specific marker for thrombosis or for clots. And that's because it is a piece of a clot that was there. So that gives notice to the doctor that they do have clots occurring. All right. And one last thing here is our coagulation pathway inhibitors. So now that we've talked about the coagulation pathways and how we clot, we've talked about how we get rid of the clots because we don't want them sitting around. We also need to talk about how do we stop our pathways. When you get those coagulation pathways started, that's great. We're going to get a clots out of them so we can heal. But at the same time, what stops them? At some point, they have to be stopped and told, that's enough. We have what we need for a clot. You need to stop. And that's the inhibitor's role. So there's 3 inhibitors here that I listed that you should know. And the whole role, again, of these is to put a stop to the coagulation pathway so that we don't keep clotting. The first one is called the tissue factor pathway inhibitor. So remember back, there was one of the pathways that had the name tissue factor pathway, and that was the extrinsic pathway. So the whole role of this inhibitor, TFPI, is to inactivate factor 7. And when you look at your pathways, factor 7 is only found in the extrinsic tissue factor pathway. So that is one way that the extrinsic pathway gets inhibited and is told to be done. So please know that TFPI inactivates factor 7. Our next one is what we call protein C-S. I mentioned a few slides ago that thrombin activates protein C, and then when protein C becomes activated, it will bind onto protein S, and they make a complex together. And together, they go and inactivate factors 5 and 8. Well, if you inactivate factor 5, that's found in both extrinsic and intrinsic pathway, right? Because that's a common factor. So that'll help inhibit both pathways. And then factor 8 is found in the intrinsic pathway only. So that'll help inhibit that intrinsic pathway. And then the last inhibitor is antithrombin. Antithrombin just sounds how it is. It neutralizes thrombin. It basically makes it so thrombin doesn't have a role. And think about how many things that thrombin does. That's a great way to inhibit our clotting pathways. And it also will go and neutralize factors 9, 10, 11, and 12. So those are all intrinsic pathway factors. So all three of these have roles in our body. Make sure that you know what factors they inhibit, and also you should know the factors and what kind of pathways they go with. All right, and the very last slide is, it looks a little intimidating. It's not nearly the same as my drawings. It comes out of Wikipedia. Some people love this drawing and chart. Some people hate it. Like when you first look at it, it looks like, holy crap, I can't figure this out. But it contains everything that you guys ever should need to know, too. If you look over here, this is your intrinsic pathway, and it starts with 12, and it has it going down through the common. The common starts right here with 10. Over here is our extrinsic pathway starting with factor 7. That also jumps down over to 10, and then you get your clot at the end. So it's just got the pathways put together. In red here are all your inhibitors, and they show where they put stops or what they inhibit so that the pathways will stop. So it just basically has all that information together on one chart. If you like it and it helps you, great. If not, ignore it and don't use it. All right, so any questions regarding this chapter 40 and any of the material we went over? It's a ton of information. But anything coming up for you guys yet? Okay. Do you feel like it's a little bit more understandable? All right. You know what? Some people actually find the complement pathway easier than these pathways. I prefer both of them. I like them all. You know what? When I first learned coag in school, I hated it so bad. But then when I went back to it, I really loved coag. It's a very complex little area that kind of grows on you. I always say it grows on you like a rash. You just have to love it. But I'm glad that you're finding that these are easier to understand rather than complement. So at least this is clicking. I'm going to stop the recording, and then I will go on and